السلام ورحمة الله وبركاته. Let me share my screen. This class we started looking at the theory of groundwater, okay, where we define groundwater, hydrology, and the role of civil engineers and the hydrogeologists when it comes to the issue of groundwater. Define porous media and the constituents, and then we look at the subsurface classification of surface water, okay, this unsaturated to the saturated zone, and they look at the different zones of porous media. And we briefly explain the surface water versus groundwater in terms of quality, quantity, sustainability, and all that. Yeah, we were explaining the water-bearing formation called aquifer. Okay, basically the soil or rock, within which you find water, because in the subsurface, more often than not, it is not like, let's say, in the rivers and oceans in which you have water alone, okay, filling a whole space. But in the subsurface, you normally have soil, rocks, and other geologic formations. So the water-bearing formation here we call aquifer, simply like a soil or rock, but it has to be able to furnish appreciable amount of water to wells. Okay, and the quality of such rocks as an aquifer depends on the extent of such occurrence. Sometimes they form highly permeable aquifers. Okay, so that you get good amount of water. Okay, and generally we have metamorphic and igneous rocks, which are in solid forms and sub-poor aquifers. Okay, metamorphic and igneous rocks. Basically, rocks are classified into three. You have metamorphic, igneous, and sedimentary rocks. Metamorphic and igneous rocks, they do not have, good cracks that will ensure good permeability and connectivity of the holes. Okay, but sedimentary rocks is a very good aquifer. Okay, so metamorphic and igneous rocks are poor aquifers. Okay, similarly, clays, although having a high level of porosity, to be poor aquifers because their pores are too small and not well connected. Clay has a lot of holes, but the holes are not connected. Okay, if they are not connected, it means you cannot have continuous flow of water from one hole to the other. Okay, and that is a problem as far as good aquifer is concerned. So you have fine sand, you have clay or silt, medium, and you have coarse sand. Okay, so that's why you have this figure. Fine sand is one whose size is very small, okay, such as clay material, and then you silt. Silt, the size of silt is slightly that of clay, the grain, the size, okay, and you have medium sand, and then you have coarse sand, which are the bigger ones. Usually sizes less than 1 millimeter. Clay are usually classified as those grain sizes less than 1 millimeter. So clay is poor aquifer, okay, because although it has high level of porosity because of the small size of the grains and the pores, but the pores are not interconnected, are not well interconnected. Now, still on the aquifer, the horizontal extent of an aquifer is much larger than its thickness. Okay, meaning the thickness of an aquifer compared to the horizontal extent is very small. Okay, it doesn't mean that it is just few centimeter. Yeah, it can be so many meters, but when you compare to the horizontal extent, okay, meaning the horizontal coverage of that aquifer may be in kilometers, meaning I mean several hundreds of kilometers, while the thickness may just be, uh, let's say, some few meters, maybe 100 meter, or even 50 meter depth. Okay, for instance, the aquifer here at Hafubab is we have the Dammam aquifer. Okay, we Dammam aquifer, all the way from Dammam, and from here is 500 kilometers. 500 kilometers. Okay, so the horizontal extent of aquifers are much larger than their thicknesses. Okay, so always think of an aquifer as a thin layer. Always think of an aquifer as a thin layer. Okay, so other geological formations. Aquifer is one of the geological formation. Okay, but then, like I said, we have aquifer is one that amount of water, while others that do not give good amount of water, they have other names. Okay, the first here we have aquitard, e.g. sandy clay. They leak water vertically to adjacent aquifers. Okay, aquitard. Okay, it may leak water vertically to adjacent aquifers. Then we have aquiclude or aquifuge. Okay, and this one's example you have unweathered, unfractured granites. Okay, which they don't have any hole. I mean, they don't contain water, neither do they allow water to pass through them. So that's why aquiclude, they exclude water. Okay, for all practical purposes, an aquiclude may be considered as an impervious layer. Impervious layer meaning impermeable, meaning water cannot pass through it. That is impervious, that is impermeable. So, let me see. All right. Aquiclude, they play a role in formulating boundary conditions, okay, because it is no flow boundary, okay. So this is like an example, that is leakage at this point. If you look at it, let me use the red pen so that it will be clearer. Where is can I change the color? View. The pen option is not displayed. All right. So here, aquitard, it can leak water to adjacent aquifer vertically, but it is also, I mean, conducting water. Okay, and this is also an example of an aquitard. Yeah, because there is leakage vertically. Okay, up, down, and then this is patched aquifer. When you have an impermeable, material, that in the unsaturated zone, so it can hold some water. So this is called patched aquifer. Patched aquifer. Now, someone may ask, where do aquifers get their source of water? Yeah, they get their source of water from the ground surface, from recharge areas. Okay, from recharge area. If you look at this here, this one, okay. This area here called recharge area in the far left end. Okay, when rain falls, or as a result of artificial activities, anthropogenic activities, when you pour water, it sinks to the ground, it filtrates, isn't it? If it is enough quantity, it seeps deeper down until it reaches the groundwater table. Okay, until it reaches the ground. table. So that serves as the source of water. Okay, you can see this aquifer, is bounded by aquitard from above and below. Okay. You have aquifer A, aquifer ABC. Aquifer ABC. Let's start with aquifer A, which is the first one that you reach, where you have the groundwater table. Square right, to the right end, you can see a whose bottom is lying in unconfined aquifer. That is aquifer A. You have below the bottom of the well, then you will not have water throughout the year in your well. Because imagine the water table goes down to this level. Okay, so your well will be rendered devoid of water, it will be empty. Okay, now let's look at aquifer B. Aquifer B now is confined aquifer because it is bounded from above and below by an impervious layer. This is aquifer. Okay, so it's like pipe flow. Okay, so the water inside confined aquifer is under pressure. It is under pressure. Okay, it is under pressure, and the height to which the water can rise, okay, is called the piezometric surface. It's called the piezometric surface. It's called the piezometric surface, and that height depends on the recharge area, the water table in the recharge area. If you look at the recharge area here, this is the water table at this point. Okay, so when you sink your well inside aquifer B, the water will rise up to the up to the level of the water table in the recharge area. Okay, because that is like the pressure head or the piezometric surface or the piezometric head. You remember in fluid mechanics, we discussed about piezometric head and piezometric pressure, where we said the piezometric head is given by P over gamma plus C, elevation head plus pressure head. Okay, elevation head plus pressure head. So this is the piezometric head. Okay, and the piezometric pressure, P subscript Z, is simply gamma times the piezometric head. Okay, so these wells could serve like piezometers. You remember when we were discussing about the different ways of measuring pressure, in chapter 3 of fluid mechanics, CE 233. We discussed that pressure can be measured using about 4 different methods. Okay, one of them, okay, is what? Who can remember exactly what we mentioned about the different methods of fluid mechanics? All of you passed the course, so It's time to show whether you really, retain the knowledge you obtained, in the course. Yes, I can hear you.
Doctor, again, what you said?
What are the different methods by which we can measure pressure? Pressure. This we discuss in fluid mechanics. What are the different methods for measuring pressure? Because that is what, although fluid mechanics is not prior to this course, but it's when we are currently reviewing syllabus, and fluid mechanics has got to be a prerequisite to this course. Yes, what are the different methods of measuring pressure? In the fluid statics, we look at all these methods. The first one we mentioned was barometer, isn't it? Which is just a tube, inverted tube, okay? Oh, not the formula. Someone is writing formula for pressure, saying force times area, and pressure is force times area. Pressure is not force times area. Okay? So the various methods of measuring pressure, one, you have the barometer, okay, which is an inverted tube. You can fill it with mercury, which will rise to 760 millimeter, which is equivalent to the atmospheric pressure. And you have the Bourdon tube gauge, and you have the piezometer and manometer. Okay, the piezometer is simply a tube inserted in pipeline, okay, in which water rises, and the height of water is the pressure inside the pipeline. Okay, so that is corresponding to the piezometric height. Okay, it is corresponding to the piezometric head. And the same thing when you sink a well, it's like a piezometer. It's like a small tube inserted in a pipe. So the height which water rises gives the piezometric surface or piezometric head. Okay, so water inside a confined aquifer is under pressure because it is bounded above and below, and the head is way higher up, at the recharge area. This is the recharge area. You can see the water table. So when you sink well, water will rise up to the height of the water table at the recharge area. Okay, and sometimes depending on the topography of the ground surface, you can have the water even gushing out of the surface, which we call flowing well. Look at the flowing well in the middle. This is called flowing well because the piezometric surface is above the ground surface. So when you sink well, water will gush out without using any pump. Without using any pump. It's called flowing well or artesian well. Artesian well. You can see it, artesian well. Okay, so this is leaky. Okay, this is confined aquifer because the well has reached aquifer B and aquifer C as well. And this is the water surface, the piezometric surface of aquifer C. So water will rise at whatever point you sink well, water will rise up to that surface. Okay, water will rise up to that surface, up to the piezometric surface. And this is also recharge area for the unconfined aquifer. This is recharge area for the unconfined aquifer. Okay, this is leaky aquifer because water can pass through the impermeable layer. So I think, yeah, I have said, I think, enough on this. If there is anything, I will come back to it later. Now, types of aquifers. Okay, aquifers are referred to in different ways. Okay, I just mentioned the MAM aquifer, which is because of the MAM. Okay, according to the type of material of which the aquifer is made. Okay, for instance, we may speak of sandy aquifer or limestone aquifer. This is telling you the geologic formation that the aquifer is made up of, meaning it is made of sand. The other one, limestone. Okay, and we can define aquifer according to the geological age of the layer, e.g. Pleistocene aquifer. Okay, this is geological age of the aquifer. And we can define aquifer according to the local name given to the geologic layer. For instance, we can call of Zaria Aquifer. Zaria is a town, okay? It's my hometown. We have Zaria Aquifer here. We have the Mam Aquifer. We have Maruduma Aquifer. We have Riyadh Aquifer. So we have a lot of aquifers named after different towns here in Saudi Arabia, okay? And it can be named according to the presence of confining layers, okay? And here we have confined aquifer or unconfined aquifer and patched and leaky aquifers. This I explained in the previous figure. Confined aquifer is confined from above and below by impervious or semi-impervious layer, and patched aquifer is confined but from below by impervious layer, although it did not join the water table yet, it is in the unsaturated zone. And then you have leaky aquifers. Okay, leaky aquifers in which the confining layers are semi-impervious layers, meaning they allow vertical movement of water to and from the aquifer. Okay. Now, fluid potential and head. I just mentioned the hydraulic, piezometric head. Okay. So here we have the fluid potential, which is the energy quantity per unit mass. The energy quantity per unit mass. When you have fluid flowing, then it possesses energy. Okay, and that is the fluid potential, which is the energy quantity per unit mass. So the fluid potential at any point is given by GH. So this is simply like the potential energy, because it's per unit mass. Potential energy is mgh. Okay, so when you divide by the mass, you have only gh. So you have h to be the energy head at that point. Okay, the energy head at that point, which is the height to which water can rise. And flow of any kind occurs from a region in which the potential has a higher value towards the region of a lower value. So there must be potential gradient. Okay, potential gradient. You know, just like heat. Heat flows from region of higher concentration or higher capacity to where you have lower capacity, or from hot to colder region. Okay, the same thing, water flows from region of higher energy to regions of lower energy, and it flows from a region of higher to regions of lower pressure. Okay, what are you writing? J m squared over L. What is J times m squared over square per second? Ahmad Muhammad, you wrote J times m squared per second. Hmm? What do you want to say? Unit of what? Unit of what? Of fluid potential. Okay, we can get the unit. Okay, we can get the unit. It can just be joule because it is per mass. So it's the energy per unit mass. Okay, fluid potential at any point is the energy per unit mass. Energy is in joule, so it can be just joule per kilogram. Okay, joule per kilogram. That is energy per unit mass. Otherwise, let's see. E is in meter per second squared. H is in m. So it is meter squared per second squared. And that is why the dimension is L squared over T squared. Okay. So you can use this, or you can use joule per kilogram. Okay. Because it is the energy per unit mass. So either using joule per kilogram or meter squared per second squared. Oh, okay, it's M, not G. Okay, all right. So you must establish potential gradient before you have fluid to move from one point to another. Okay, fluid moves from region of higher concentration, higher energy to regions of lower energy, regions of higher pressure to regions of lower pressure, not the reverse. Okay. Now, H is equal to Z plus this Z is the elevation at a point with reference to a datum, and this pressure head, the pressure above atmosphere at the point, pressure above atmosphere, which is the gauge pressure. Okay, I just mentioned, this is just the piezometric head. Okay, it's just the piezometric H equal you done an experiment in which he has a sign and water is flowing at a rate Q. So this is the datum. This is Z1, Z2. Okay, and when you sink a piezometer, water will rise to this level, which is the head of this point. This is the pressure head at that point. Okay, so lagging. What do you mean by lagging, Khalid?
So your network is disconnect when you explain the last things.
Oh, this last slide.
Yes, yes.
Okay, so you did not hear me.
No, no, it's disconnect.
Okay, then let me explain it again. So I hope now you can all hear me clearly. Can you all hear me clearly? All right, all right. So let's move on. So, like I said, Darcy is a 19th century French engineer who experimented with sand filter media, one of the treatment plants. Okay, here you have a tube in which you have sand. Water is flowing through the sand at a rate equal Q, the flow rate. Okay, and here you use meters to measure the pressure change at a distance at an interval. Okay, of course, as water flows, it will be losing energy, so the pressure head is going to reduce because the pressure head is simply the energy per unit mass. Okay, is the energy per is the fluid potential, okay, which is the energy per unit mass. So the energy will be reducing because of flow, because of friction, okay, and a lot of other factors. So the pressure head is going to reduce. It's going to be here. It's going to be here than downstream. Okay. Now, Darcy made the following observations, which I will explain in the next chapter. In the next slide. Okay. Basic equation of groundwater flow, the Darcy's law. Okay. The fundamental law of groundwater movement was discovered by Henry Darcy in 1856. Okay. He realized that the flow rate is directly proportional to delta H. Okay. The flow rate is directly proportional to the difference between the heads. Okay. This is H1, H2. Okay. Call this H1, H2. Okay. Meaning as the flow rate increases, you have delta H also increases. And they also realize that it is inversely proportional to the length of the tube. Okay, the length of the tube, okay, which is L. the interval between the pressure heads, okay? So meaning the flow rate increases. As the flow rate increases when the length is short, okay? While for longer length, the flow rate reduces, okay? And then the cross-sectional area, okay? So in general, because delta H over L is what is called hydraulic gradient, okay? I just mentioned of the potential gradient, isn't it? You must establish a potential gradient before fluid flows, okay? So the change in the head, the pressure head, okay, over the length is called hydraulic gradient and is designated with small letter I. Okay, it's designated with small letter I. And so when you combine these three equations in one, you introduce a constant, which is K, which is the hydraulic conductivity. Okay, so when you combine all these proportionalities, you have Q equal Ka in minus H2 over L. Okay, here we said H1 minus H2 because the head is higher upstream than it is downstream. Okay, it is higher upstream than it is downstream. Some texts may use minus. Okay, I'm going to explain that. H1 minus H2 of L is the hydraulic gradient, and the flow rate per unit area is small q now. When we divide by the area here, okay, small capital Q over A, okay, so which is K delta H over L, which is also called specific discharge or seepage Darcy velocity or discharge velocity. Okay, it's called specific discharge, Darcy velocity or discharge velocity. When you see the unit of small q is given in velocity, okay, the dimension is L over T, which is the same dimension as velocity. So it is called specific discharge because it is discharge per unit area. It is called Darcy velocity because it gives the velocity of the flowing fluid, okay, although not in an open channel, because here you have porous media. Here you have porous media inside, okay? Here you have porous media inside, and it is also called discharge velocity. A negative sign is inserted on the right side of equation 3.4 if delta H is taken as H2 minus H1, thus indicating flow in the direction of decreasing head. If we change this H2 minus H1, meaning H2 minus H1 is going to be negative. So for the flow to be a positive quantity, we need to introduce a negative sign so that Q will turn out to be positive. Okay, and that indicates the flow is in the direction of decreasing head. Okay, and as the flow progresses, the pressure head is reducing. Of course, this is due to friction factors and other considerations, but mostly you have losses due to friction. As water is flowing, it is losing energy. Just imagine yourself walking, walking from here to, let's say, Al Makan Mall. Okay, the energy you started with, you will not end up with that energy, definitely, because as you are walking, your body is utilizing that energy to do a lot of things, and then you'll be losing energy along the way. You'll be sweating, you will be breathing. All these, activities take a lot of energy from you. The same thing with water. When flowing, it loses energy. Okay. Darcy velocity and seepage velocity. Okay, so we mentioned that small q or v is called Darcy velocity. Okay, but that is different from the seepage velocity. Okay, it's different from the seepage velocity. V is known as Darcy velocity. It's a fictitious velocity since it assumes that the flow occurs through the entire cross section of the material. It assumes that the flow occurs through the entire cross section, whereas the flow is actually limited to pore space only. When you have a pipe in which you have only water, the flow takes place throughout the cross section, isn't it? But in this case, the cross section is not empty. You have porous media, you have sand inside. So the flow will take place only through the tiny spaces between, the soil, between the grains. Okay, so it's not like an actual velocity per se. So it's like an apparent velocity. That's why we call it Darcy velocity. So if we want to actually know the seepage velocity, we need to correct, we need to take care of the area by introducing porosity. Okay, so how do we do that? VV is the seepage velocity. Okay, V subscript V is the seepage velocity, and A subscript V is the area of the voids. Area of the voids, that is area of the spaces within the soil sample. Okay, void is the space within the soil sample. Okay, then from continuity equation, remember in fluid mechanics, we did continuity equation. Q is equal to AV, which is equal to A subscript V and V subscript V. Okay, so what we are saying is that since the flow is continuous, okay, so the continuity equation holds. So A times V is equal to, that is the flow within the entire area, the cross-sectional area times the seepage velocity is equal to the flow within the tiny spaces of the voids, okay, where we have the seepage velocity. And here we made V, subscript V, the subject of the formula. Okay, A is the total area of the cross section. Okay, while V is the void, area of the voids. Okay, now multiplying both sides of the medium by L. Okay, we multiply by L. Here we have volume. Area, the cross section area times length, we have volume. The cross section area of the voids times L, we have the volume of the voids. Okay, and what is porosity? Porosity is simply the ratio of volume of voids to the total volume, okay, and that is porosity. Volume of voids of the total volume. Okay, so meaning V will now become K delta H N. This is eta L. Eta is the porosity. Okay, eta is the porosity. So now V subscript V is the seepage velocity. What have we done in essence? We divide by the porosity. We divide the Darcy velocity by the porosity. When we do that, we get the seepage velocity. Darcy velocity is the velocity flowing, that is generalizing, it's overgeneralizing the flow. Okay, it's assuming the flow is occurring throughout the cross section, while in real sense, in practical terms, the flow occurs only through the tiny spaces, through the void spaces. So to find the actual seepage velocity flow, that is why we are correcting Darcy velocity to get the seepage velocity. So the seepage velocity is equal to Darcy velocity over the porosity. Okay. Now let's take some few examples here. A channel runs almost parallel to a river. Okay. The channel runs almost parallel to a river as shown in figure 5.4. So this is model of river and channel. Okay. Model of river and channel. Okay. And the water level in the river is at elevation of 120. So this is the river. This is the river. Okay. The elevation of water is at 120 feet. And in the channel, okay, at an elevation of 110. So you have river flowing and you have a channel flowing. And the water level is at an elevation of 110, above that. The river and channel are 2,000 feet apart, the distance of separation between them. And a pervious formation. Pervious meaning water can pass through it. Okay, that is pervious. Semi-impervious, it means it allows water to pass, but not all the time. Okay, not all the time. Meaning it partially allows water to pass through it. And impermeable, pervious material means it does not allow water to pass through it at all. Okay. So you need to understand all these words, because I know sometimes, in exams, some of you may be asking the meaning of words. What is the meaning of this? Okay, so we can use different words. semi-impermeable, permeable, and impermeable. Okay, or we can use pervious, semi-pervious, or impervious. Okay, and if formation is 2,000 feet, okay, with an average thickness of 30 feet and hydraulic conductivity of 0.25 feet per hour joins them. Okay, so this is the pervious medium. The thickness of the pervious medium is 30. Okay, determine the rate of seepage of flow each day from the river to the channel. You can see that the river is at higher elevation, so water will seep from at higher elevation, meaning it is having higher energy, okay, and higher pressure as well. So water will seep from the river, to the through the pervious medium to the channel. Okay. So the question is asking us to determine the rate of seepage of seepage flow each day from the river, okay, to the channel. And simply here, if we consider this, it is a 1 feet width. If we consider the width to be 1 feet, okay, that is the width of the river channel perpendicular to the paper, okay, perpendicular to the paper, the area of cross section of the aquifer, okay, area of cross section of the aquifer, that is this aquifer that's allowing water to pass through. Okay, if we consider the width to be 1 feet, so we need to find the cross-sectional area. Okay, the cross-sectional area 30 times 1. Okay, if we assume 1 feet, and then from there we were given the hydraulic conductivity, which is K. Okay, 0.25 feet per hour. But don't forget, we were asked to find per day. Determine the rate of seepage flow each day from the river. Okay, so we are given cross hydraulic conductivity in feet per hour, so we need to convert it feet per day by multiplying 24 hours over 1 day. Okay, so this is 6 feet per day, and then we apply the Darcy's equation, which is Q, okay, equal Ka H1 minus H2 over L. Okay, the head, the elevation of water in the river and the channel will serve as the head. Okay, H1 minus H2, L, the distance separating them, 2,000. Okay, area is 30. We assume a unit thickness, and then this is K. Okay, and this is 0.9 feet cube per day per feet width. Okay, per feet width. Remember, we assumed a unit width here. Okay, we assume 1 feet width. Okay. I hope it is clear. Now, this is another example. Okay, good. This is another example which says a semi-pervious layer, okay, which is an aquitard, meaning it barely allows water to pass through it, okay, separates an overlying water table aquifer from an underlying confined aquifer as shown in figure 5.5. Determine the rate of flow taking place between the aquifers. Okay, so here you have vertical downward flow through a semi-pervious layer. This is the water table at point at A, the water table. You have well, piezometric surface, well is sunk inside. You have B, you have C. This is a semi-pervious layer, and we have its coefficient of its hydraulic conductivity, and this confined layer. So the semi-pervious layer and the confined aquifer, they all have different hydraulic conductivities. Of course, we should expect them to have different hydraulic conductivities because hydraulic conductivity, as I explained on chapter 4, is the ease with which water flows through the soil. Okay, that's if you look very well, the value for semi-pervious layer is the smallest, 1 feet per day. meaning water can travel a distance of just 1 feet in 1 day, while for the water table aquifer or the unconfined aquifer, the water can travel up to 40 feet per day, and in the confined aquifer, it can travel up to 50 feet per day. Okay, so it definitely tells you that water can easily move in the confined and unconfined aquifer than in the semi-pervious aquifer. Okay, so this is the practical meaning of these different values of the hydraulic conductivity. So now, here we want to determine the vertical downward flow through a semi-pervious layer. Okay, since the water table is above the piezometric surface, okay, the water table is above piezometric surface. Where is the piezometric surface? This is the piezometric surface of confined aquifer, meaning this is the height to which water will rise in a well. You can see that this well has penetrated the confined aquifer, and water rises to this level. But the water table is above the piezometric surface. The water table is now the piezometric surface of the unconfined aquifer. Is the piezometric surface of the unconfined aquifer. So since the water table is above the piezometric surface and a semi-pervious or leaky layer exists, flow will take place from the water table aquifer to the confined aquifer. Okay? Flow will take place from the unconfined aquifer to the confined aquifer because pressure is higher. Okay, there is higher pressure in the unconfined aquifer than in the confined aquifer. Okay, so the flow is always from higher pressure point area where you have higher pressure to point where you have low pressure, and head loss will take place when water moves through water table. That's top aquifer, which is not known. That is the head loss, and then assume that the head at point B. Assume that the head at point B shown in the figure is HB, and consider the unit horizontal area through which flow takes place. Point B specifically is the top of the semi-pervious layer. Okay, so if we assume the head at that point to be HB, okay, so here between points A and B, point A is the water table and point B is the bottom of the unconfined aquifer. Okay, B is the bottom of the unconfined aquifer. So what is the flow per unit area? Here we are considering unit area. That's why here we said unit horizontal area. Here we use small q. Okay, we use the Darcy's formula, which is K. 40 is K, which is the hydraulic conductivity for the unconfined aquifer. Okay, and we have the head of the unconfined aquifer, which is 80 plus 10. You see, the head here of the unconfined aquifer is 90. 80 plus 10. So that's why we have that 90. Okay, and minus head at the top of the semi-pervious layer, which is HB, and the length, okay, over the length, and the length is 90. Okay, the length is 90. The distance between the top of the water table and the top of the semi-pervious layer is 90. Okay, so having generated this, we now go ahead and consider B and C, that is the semi-pervious layer. Between points B and C, with reference to datum C, okay, the head at C equals the piezometric surface, the piezometric level above C. Okay, the head at C equals the piezometric level above C. That is 80 plus 15. Okay, that is 80 plus 15, because here in the confined aquifer you have the head to rise up to 80 meters above point B. So 80 plus 15 will give us the head here at C. C falls within the confined aquifer. Okay, so that is the head. Okay, And then the head at B equals HB plus datum head, okay? And the datum head is 15 feet, which is the thickness of the semipervious layer, okay? So here we have HB plus 15 minus 80 plus 15 over the thickness, which is 15, okay? And don't forget K for the semipervious layer is 1, okay? K for the semipervious layer is 1. So we now equate this. The flow Q here is equal to Q here. What we're looking for is HB, okay? What we are saying is the head of this point given by HB 15. The pressure head here plus 15, okay? And C here, the head here, which falls within the confined aquifer, is simply 15 plus 80, which is the height of water in this well, which penetrated the confined aquifer. So when we equated these two, we can find HB, which turns out to be 88.7 feet, okay? And once we find the head, we can substitute in either equation 1 or 2 to find the flow rate per unit area. And when we do that, we have 0.58 feet cubed per day per square foot. Okay? Feet cubed per day per square foot. Okay? And this is because Q is in per area. So that is why we have this per square foot. Okay? Because Q is simply the small q is capital Q over area. Is that clear? And then this is another simple example which has a confined aquifer, okay, which has a source of recharge as shown in the figure. This is the source of recharge. Okay? So this is a confined aquifer. So this is a impermeable layer. This impermeable layer. You have wells dug to the confined aquifer at a distance of 1,000 meters. Okay. So the hydraulic conductivity of the aquifer is 50 meters per day and its porosity 0.2. Okay. The piezometric head, porosity is a measure of the voids, okay, of the void space. It's simply, as I defined earlier, is the volume of voids over volume, the total volume. Okay, so it's giving you like a measure, like what percentage of the voids of the space of the area is occupied by voids. So the higher the porosity, the more voids. Okay, the higher the porosity, the more voids you have. Okay, void we mean spaces, internal spaces between, I mean the spaces between the soil grains, the porous layer in particular. Okay, so the hydraulic conductivity of the aquifer is 50 meters per day and the porosity is 0.2. The piezometric head in two wells 1,000 meters apart is 55 meter and 50 meter. Okay, so this is lower, this is 50 meter and this is 55 meter. Okay, because as flow, you know, it's losing energy, so that's why it's not at the same height. Okay, from a common datum, the average thickness of the aquifer is 30 meter and the average width, the thickness 30 meter and the width is 5 kilometer. Determine the rate of flow through the aquifer and determine the time of travel from the head of the aquifer to a point 4 kilometer downstream. Assume no dispersion or diffusion. Dispersion and diffusion will explain in the next chapter. They have to do with contaminant transport mechanisms, okay? The different ways by which contaminants can flow, okay? So now, we were given the width and the thickness of the aquifer. So the area of cross-section of flow is determined to be 335 kilometers. So we are converting the kilometer to meter here, okay? So this is the area of cross-section. And then the hydraulic gradient, which is simply H1 minus H2 divided by L, okay, is determined here using the height of water within the wells, okay, the hydraulic gradient. And the first part of the question is asking us to find the rate of flow through the aquifer, which is Q. So we use the Darcy's law, okay. So Q is simply KI, okay, KIA. I, the hydraulic conductivity, okay, Kia. K is 50 meter per day. I is already determined above hydraulic conductivity. A is also determined above. So this is the flow rate, meter cube per day. And to find the, and then the second part of the problem says we are to determine the travel time from the head of the aquifer to a 0.4 kilometer downstream. Okay, so first we need to determine Darcy velocity, which is capital Q over A. Okay, what is this? And then we can define the seepage velocity. Okay, and to find the seepage velocity is given by the Darcy velocity over T. So this is the seepage velocity. You can see that all the time the seepage velocity is higher than the Darcy velocity because it is through tiny openings. Okay, the area is small, the velocity has to be higher according to the continuity equation, Q equal AV. Okay, AV is constant. So when the area of flow is smaller, then the velocity has to be higher to maintain the same flow rate. Okay, so all the time, you realize that the seepage velocity is higher than the Darcy velocity. See the Darcy velocity to be 0.25 meter per day and the seepage velocity 1.25 meter per day. That is 5 times greater than the Darcy velocity. Okay, so to find the time of travel, we use the velocity, the seepage velocity in this case, not the Darcy, because that is why we found the seepage velocity. No, velocity is simply distance over time. Okay, so we want to find the time. We know the distance, we know velocity. Okay, so we simply substitute. Okay, to find this is 3,200 days, which is 8.77 years. Okay, this demonstrates that water moves very slowly underground. Okay, it moves very slowly, sometimes 0.1 meter per day. Okay, 0.1 meter. The velocity of flow for groundwater is very slow, very slow. You can have it 0.1 meter per day, 0.2 meter per day. Okay. And here are some additional readings. Okay. Additional references. Now, any question on this before we move to the next chapter? We'll take some break. If you don't have any question now, take some break and then we start the next chapter. All right, so let's take like 5 minutes break and then we come back. So we are back. Now we'll move to the next chapter, which is the Contaminant Transport. Okay, chapter 7. Okay, the intended learning outcomes. Students at the end of this chapter will be able to explain the dissolved contaminant transport processes and understand the occurrence of saline water intrusion and upconing. Okay, this is a picture showing some source of contamination in groundwater and how the different processes, different modes of movement of the contaminant. Okay, of advection plus dispersion or diffusion plus suction or retardation, gradation. Okay, we'll explain these processes. Okay, I'm on the second slide. Can you see the second slide? I'm using the presentation mode now.
No, doctor, we can only see the first one.
Then I will have to presentation mode. I don't know why it is not showing the trans. I think what will happen, I will try another browser to see if it will work. Maybe I will try Edge, Microsoft Edge, to see if something different will happen. Because the Chrome is having issues now. Then this is the Firefox that I'm using. It's also giving me some, not working as smoothly as the Chrome used to. So let me use the slide not in the presentation mode. So transport processes, like I said, this is contaminant transport. Contaminant is, anything in water that is not water. Okay, there is difference between contaminant and pollution. Some people may look at the two words to mean the same thing when we are referring to water, pollutant and okay, but actually pollutant and contaminant are different. Okay, anything in water that is not H2O. Water is the chemical formula for water is H2O. Okay, so anything in water that is not H2O is considered as contaminant. Okay? Then it depends if it has harmful consequences on our health, then we call it pollutant. Okay, if it changes the color, the taste, and it can impact on our health, then we call it pollutant. Okay, but anything in water that is not water, okay, is called contaminant. So in this case, whenever you take any bottle of water, when you look closely, it will show you the ions. It will write anion and cations. Okay, and there you will find a lot of ions, a lot of minerals with the associated concentration. Okay, you will see sulfates, chlorides, fluorides, nitrate, sodium, calcium, magnesium, potassium, iron, So all these are dissolved minerals inside water that we drink. Of course, they have they enhance our health. Okay, yet they are also considered as contaminant. Okay, anything in water is not water. But then you can also have pure H2O. This can be produced in the lab, which we call distilled water or deionized water. This you will discuss more in environmental engineering course, CE. In the lab, for most of the laboratory purposes, we use water that is free of any contaminant. It does not have any dissolved minerals. Water that is purely H2O. And to get that type of water, we need to distill the water, to heat the water and collect the vapor and condense it. Okay, because the ions do not vaporize with the water. Okay, sometimes if we truly want to get a completely pure water, pure in that you have only H2O, then we have to go further and use what is called deionized water. Deionized water is obtained using what is called reverse osmosis, RO system. Okay, that system like completely removes all dissolved minerals, all dissolved salts in the water, so that only H2O can pass through. It has tiny filters, fibers, that only water can pass through. Any dissolved mineral cannot pass through it. Okay, so you have distilled water, you have deionized water. All these are, pure H2O, pure water, okay, that is free of any contaminant, and that's why I'm taking my time to explain the difference between contaminant and pollutant. Okay, contaminant is the general term that is referring to any water which is not H2O. Okay, and pollutant is that substance in water which negatively impacts on our health, which affects our health. Okay, which affects our health, like germs, like pathogens, okay, viruses, bacteria, fungi. All these, when we drink water with bacteria, more often than not, although we have useful bacteria, but we have others that can impact on our health. Okay, so this you will discuss more under the environmental engineering aspect, because that is how discussing about the quality of water. Here in water engineering, we are looking at the quantity. We are so specific about the quantity. But then, even the contaminant transport is somehow like in between the environment and water, because in the contaminant transport, we are looking at the transport of these contaminants along with the flowing fluid, along the flowing water. We are not really, we sometimes when you're considering the processes, so it's one area that, like, in a way, is in between water and environment, or it combines, the two principles. You need to have the knowledge of the two areas, water and environment, because water, the mechanics of flow of water in the subsurface, in the groundwater, in the subsurface, you need to understand, the principles of hydraulics and hydrology as well. And then when you have contaminant introduced in the water, it will affect the transport mechanism. Okay, it will affect the quality sometimes if it is a pollutant. Okay, so you need to have understanding also of the environmental engineering, because of the behavior of the contaminant are different. We have different contaminants. The way they behave in the subsurface or in the groundwater is also different. Okay, and this we are all going to explain further. Okay, so transport processes. Okay, the first and the simplest one that we are going to explain is the advective transport. The advective transport. Okay, all dissolved and suspended matter gets transported in water by the influence of spatial energy gradients. I mentioned in the previous chapter that you must have energy gradient, okay, potential gradient, before water can move, okay, because it moves from region of higher energy to region of lower energy. And I just finished explaining that if any water, just take any bottled water, and in the label, you will realize they will give the constituents of the ions dissolved in that water, the anions and the cations. Okay? All these anions and cations, they have that are dissolved in the water we drink. They usually have, they positively impact our health. They positively impact our health. So many factors can contribute to these energy gradients, such as difference in water elevations. We have seen in the previous example, when you have difference in water elevation, because it means the pressure head is higher at one end than in the other, and difference and pressure differences in a system, presence of density currents, and variation of concentrations. Okay, all these are the different factors that can contribute to the energy gradients, okay, or to the potential gradient. And transport of materials takes place by a combination of different types of energy gradients. Okay, combination of different types of energy gradient. And the quantitative measure of contaminant transport is flux. Okay, flux is the quantitative measure of contaminant transport, which is the mass of a substance moved per unit area. Okay, the mass per unit area per unit time, typically expressed as gram per meter square per second. Okay, so when you consider a given cross-sectional area, what is the mass of the contaminant passing through that cross-sectional area per unit time, per unit area, and that is flux. Still, we are describing the advective transport. Okay, all transport phenomena can be classified into three major categories. Here, the transport phenomena we are referring to, like I said, is the contaminant transport. Meaning, when you have even pure water that we have, these dissolved ions, how do they move? Okay, that is even the pure water. I mean, the water we drink, which is the sweet water. And what about if you have other forms? I mean, like other contaminant. For instance, you have many fuel stations with underground storage tanks. These storage tanks, sometimes over time, they become eroded. They can leak benzene down to the ground surface. I mean, deeper down. And this benzene, this fuel, can reach the surface of the water table, and then it will be transported along with the flowing water. Okay, so how do they move? Okay, so all these are different contaminants. Like I said, we are going to look at the transport mechanisms. So transport phenomena can be classified into three major categories: advection, dispersion, and diffusion, ranging successively from macro to micro transport processes. Macro on bigger scale, okay? Micro at the tiniest scale, tiny scale, okay? More often than not, because of the fact we need to understand first transport, let's say in open channel, very well. And then we now scale it down. What about if we have porous media inside? How does the porous media affect the transport mechanism? We have just seen previously under chapter 5 that we have Darcy velocity and we have the seepage velocity. Okay, and the seepage velocity is higher and different from the Darcy velocity. Now, the transport of the material, we will explain what is dispersion, diffusion and advection. So don't worry. But now we want to start with the basic one, which is advection or advective transport. The transport of the material that occurs as a result of the bulk fluid motion. Bulk fluid motion is called advective transport. Okay, just like a plug flow, the movement, whatever, the contaminant and the water, they move together at the same forward velocity. If the velocity of flow is uniform and constant throughout the flow field, the mass block will move to the light shaded portion of figure 7.1. We are going to check figure 7.1, which is the next slide, with the concurrent movement of the fluid element. This is figure 7.1. So here we are saying that the light shaded portion, okay, will move with the concurrent movement of the fluid element. Okay, so this is source mass, okay, like a contaminant emitting mass, okay, and mass move due to advection. So the mass will just move like a plug, okay, it will move completely. That is a situation when the flow is uniform and constant. Of course, we know the flow is, even for laminar flow, there is still some variation. You still don't have a uniform flow per se, okay? You still have small variation due to some other factors. If you remember, we considered this in fluid mechanics, okay? Let's say pipe flow, okay? There is the velocity gradient, something like this, isn't it? It is maximum in the middle, okay, and zero at the boundary because of shear stress, okay, because of the fluid viscosity, okay. So it reduces in the boundary, and it is maximum in the middle. The flow velocity is maximum in the middle. So if you have contaminant, the contaminant will also equally be. They will not just move together throughout the region. When you have a source of contaminant, let's use the inlet, okay, at some point in time the contaminant will be sprayed, okay, so that is the dispersion. It will be dispersed because of the on even this velocity. But if we assume the velocity to be uniform, if this is a source of contamination, if the velocity is the same throughout, then after some time t, the same contaminant will move together, just like a plug, okay? But like I said, this is more like an idealized case, because we know in practice that we have velocity variation even for laminar flow, okay? Even for laminar flow, except that the velocity variation varies from laminar flow to turbulent flow. In turbulent flow, you have really the velocity is much way higher than that of laminar flow. I remember the Reynolds number, we use in trying to classify. Although even in course we are going to look at Reynolds number again in flow classification. That will be in the subsequent chapters. So dispersive transport. So I explained the advective transport, which is simply the transport, of the material as a result of the body fluid motion. Okay, that is under the assumption that the flow velocity is uniform and constant throughout the flow field. Throughout the flow field, we know in practice this is far from reality. I mean, this may not be obtained in real, real scenario, because of the fact that the velocity is definitely not uniform, which will take us to the next, which is passive transport. Okay, realistically, variations in the velocity field occur around some mean value, some mean velocity value. Okay, this is what I finished explaining. There is variation along some mean velocity value. Okay, this is the average. This is the variation in the field. Okay, and you may have some average. Okay, some average velocity. Okay, of the flow rate. Okay, of the velocity of flow. So here, with time, a mass of a certain volume becomes gradually more dispersed or spread out as the different fractions of mass undergo varying transport by a variable velocity regime. Okay, so this is for the diffusive transport. When you have the mass here, contaminant into, after some time, the contaminant will be spread. Okay, some will be further ahead while some will lag behind because of the velocity difference, different regime at the different point in the cross-sectional area. Okay, some of the contaminant mass will travel faster while others will lag behind, because the velocity field is not having a uniform field. Okay, this is known as dispersive transport, and dispersive transport results from several physical phenomena that contribute to variations of flow regimes. And I explain what is viscosity. Viscosity is now having different layers to have different velocity. Okay, different layers having different velocity. So you have one moving ahead of another. Then the next transport is the diffusive transport. The diffusive transport. Okay, a very large number of molecules of matter are contained within a small volume of fluid. Just imagine bringing a perfume, spreading it in your room. You can easily get the aroma at the other end of the room, okay, because of diffusion. Okay, and some of these, the same thing happen in fluid. Okay, when you have higher concentration of the contaminant, so it quickly diffuses areas of lower concentration. Some of these are fluid molecules, and others are dissolved matter molecules. Dissolved matter molecules, and these molecules move randomly in all directions with greatly varying velocities in what is known as Brownian motion. Brownian motion is haphazard motion, unidirectional type of motion. Because of their concentration of the contaminants, they tend to move to areas of lower concentration, and the net effect is that there is spreading of the matter from higher to lower concentration. Okay, and in moving fluid, advection and dispersion are important processes. When fluid is in motion, advection and dispersion are important. Okay, while diffusion occurs even when the fluid is not in motion. Even for static fluid, diffusion occurs because you have difference in concentration. Okay, and the Brownian occurs even when you have static fluid. Okay, so there's every tendency of movement of the molecules from region of higher concentration to region of lower concentration. When flow velocities are very low or the bulk fluid motion is absent, diffusion is an important contributor to transport. Okay, so this is just what I finished explaining. Okay, for moving fluid, the most important contributor to transport, you have advection and dispersion. But when it's static, okay, when the bulk fluid motion is absent, then bulk, the most important transport mechanism is diffusion. Now, mass transport phenomena. Okay, you have a mass. After some time, okay, advection alone. Okay, this is the velocity. This is the concentration. Okay, you have. Let's assume this is like a channel in which the velocity is 0 at the bottom, and then highest at the top. Because for a channel, we did in fluid mechanics, the velocity is highest at the top of the channel, while lowest at the bottom. Okay, so the velocity varies. Okay, for advection alone, we have uniform. Okay, the velocity is assumed to be uniform. This is average velocity, and every particle within a cross section is assumed to have the same forward velocity. So a mass will move like a clock. Okay, it will not be distorted. But when you include dispersion, dispersion will take care of the variation in velocity. Dispersion is simply caused, mainly by the velocity gradient. Okay, the velocity gradient is what will pull part of the mass will travel faster than the other. So it will become something like this. Okay, shape will change over time. And when you include dispersion, now, like this is advection for the concentration. So the concentration is always constant. The concentration is always constant. But when you have dispersion, the concentration reduces because it will spread out because of the velocity gradient. The velocity gradient will enable the mass to spread out. So the concentration will not be constant as when you were considering advection alone. And when you consider diffusion, again, it will spread out further. You can see this will spread out further. The concentration will further reduce. Okay, and look at the shape. Look at how it started. When you consider advection alone, this is the shape. When you consider this diffusion and advection, look at how it becomes distorted. Okay, because of the many transport mechanisms. Okay. Now we will look at the formulation, the flux. We talked about the flux, which is the movement of the contaminant in mass per unit area per unit time, okay, which is the flux. So we will look at the advective flux, the dispersive flux, and the diffusive flux, because all this will help us understand the contaminant transport. Remember, this chapter is about contaminant transport. And that's why before we understand the contaminant transport, we need to understand the fluid transport, the transport of water first. And then when we understand that clearly, then we will now visualize a scenario whereby we have contaminant inside water. Okay. Now the advective flux, which is Na, is minus V XC. Okay. Na is the advective mass flux. Okay, which is the mass per unit area per unit time. Okay, and the negative sign for the transport is because it is in the direction of decreasing concentration. Okay, the transport is in the direction of decreasing concentration. You have C to be a concentration of the substance, which is simply mass per volume. It can be milligram per milliliter or milligram per liter, as the case may be. So depending on the unit used to express the concentration. And Vx is V subscript x is the linear water velocity in the x direction. Okay, is the linear water velocity in the x direction, because we know velocity is a vector quantity. Of course, it is highest in the x direction. Okay, and for Python, sometimes, as we have seen in fluid mechanics, you can consider one-dimensional flow, two-dimensional flow, but it is highest in the x direction than in others. In other directions, I mean, the component of the velocity is way lower. Okay, and for porous media, Vx is the Darcy velocity. When considering porous media, which is our own case, that is when we have groundwater. Okay, so Vx is the Darcy velocity. Now, let's take an example to demonstrate the application of the advective flux. It says groundwater containing a contaminant flows through a cube of sand of 1 meter on each side. It enters the left face at elevation 99.99 meter and leaves from the right face at elevation 99.90 meter. The hydraulic conductivity is 1 times 10 to the power minus 3 meter per second. Assume that the concentration of contaminant is 100 milligram per liter when it enters the tube. Here, concentration can be salt. Okay, contaminant can be salt. The concentration of salt in seawater, you find it to be like 2,000. Okay, 2,000 milligram per liter. That's very high. Okay. Here it says calculate the mass flux of the contaminant due to advection. Okay? The mass flux of the contaminant due to advection. So here we also go back to our groundwater. Okay, so V here is the Darcy velocity. V is the Darcy velocity. Is Ki. We have the hydraulic gradient, which is simply this minus this. L is 1. Okay, S is already provided to be 1. That's the length of the cube. Okay, and then we substitute to find Darcy velocity. Okay, and then we have the concentration provided in the problem, the concentration of the contaminant, 200 milligram per liter, which we can convert to gram per meter cubed. Okay, because 1 liter is 10 to the power minus 3 meter cubed, and 1 milligram is 10 to the power minus 3. 1 milligram is 10 to the power minus 3 gram. Okay, so 1 milligram per liter is equal to 1 gram per meter cube. So we just substitute in the formula, okay, which is minus 0.018 gram meter square per second in the direction of negative gradient, meaning the flux is in the direction of decreasing concentration. That is the meaning of that negative sign. Is that clear? All right. The next one is the diffusive flux. Okay, the diffusive flux. Here we derive the diffusive flux based on fixed law of diffusion. Okay, and the diffusive flux is given by N equal minus D del C by del X. N is the diffusive flux, which is the mass per unit area per unit time. D as the concentration, and X is the space coordinate in which direction the diffusion is measured. Okay? D is the diffusion coefficient or diffusivity, whose unit is L, the dimension is L square per T. Okay, and also the negative sign indicates transport in the direction of decreasing concentration. the diffusion coefficients in a porous media are smaller than in a pure medium because solids hinder diffusion. Okay, solids, the solid matrix, the porous media, they hinder diffusion. So you cannot expect to have the same diffusion like in open channel or in pipe flow or in medium where you have your porous media. Okay, so the diffusion coefficients in porous media are smaller than in pure liquid medium because the higher the diffusion coefficient, the higher the diffusion. Okay, and to obtain the diffusion coefficient for porous medium from a diffusion coefficient of liquid, a constant factor of less than 1 is applied to account for the porous medium structure. So what we do, we just have the diffusion coefficient, a case whereby we have liquid, without the porous medium, and we apply a factor less than 1, like scaling it down, because it's definitely less than the diffusion coefficient in a medium where you have the alone, okay, alone without the porous media. And that constant factor is a function of both porosity and tortuosity, which is a measure of the circuitous flow path by the water molecules. I porosity, which is simply the percentage, which is giving us like a measure of the void spaces in a porous medium. Okay, the higher the porosity, the higher the voids in that porous medium. Then we now have another term here called tortuosity. Tortuosity, elements, the liquid water, I mean, through, zigs, tortuous nature. Tortuous means not straight, something like a zigzag fashion. Fashion. Okay, so that is the tortuosity. So that factor is a function of porosity and tortuosity. My time is almost up, so I think in the next class I will look at this. Let me just look at this example because, well, I will leave it for the next class. Slide 13. This passive flux, and then saline water intrusion and upconing. Okay. So, any questions? Remember, I still have to make, a make-up class. Okay. This week I will have to find time to make that make-up class. Okay. For the class that we missed on week 4 because of the problem we encountered on the blackboard. Okay. So I will produce a make-up class. I will announce the time. Okay. For anyone that is available during the time, he can join me, or he can view the video later, but you must view the video. Okay, you must watch the video because what we cover in the makeup class will not be covered again. Okay, and our major is coming up next week. Okay, so see you for the lab. Okay, our lab today will be in the geotechnical lab. You know where the water lab, so just go straight down. When you go straight down, the last lab at the end, like where the computer lab used to be. Okay, it's like a building for the computer lab, but that is where our geotechnical lab is. Okay, so that is where we are going to conduct our experiment today, which is on hydraulic conductivity. Okay.
Doctor,
See you. Yes.
to use S better than PowerPoint.
I can't hear you clearly.
To use S better than PowerPoint because we have Ben in PowerPoint.
What?
Because you have Ben in PowerPoint, because you can use comment and you can drawing freely.
Training.
You can use Ben in PowerPoint better than in PDF. You can use Ben better than PowerPoint. You can draw.
In what? In what?
In PDF.
In PDF. Okay.
because you can convert
all right.
PowerPoint to PDF, and open PDF is better because you can drawing, you can do many things.
Yeah, I will check it, but I don't know why, because even my previous yesterday, I don't know why it's not uniform. Like yesterday, I delivered my fluid mechanics lecture. I used my pen on PowerPoint just the same way I was trying to use it here. Although even here I use it, but except that I couldn't change the color. But I will try to find another browser. I will test it to see if it will work fine, you know, because in the presentation mode, it makes you more organized.
Okay, doctor, because you know when you explain the pen, it's not clear.
Oh, which one?
The color, black color, when you explain, it's very
Oh, the black
light.
color. Black color.
Yeah, it's very light. It's
Okay.
red is better.
Yeah, yeah. I will try to see what I will do on that before our next lecture. Yeah. So, okay. I'm trying to. Yeah, the lab number for the geotechnical, the, the geotechnical engineering lab. We'll just type it now. Uh, 0510. Number for the geotechnical lab 0510. Okay, this is the lab number. All right, see you.